to Saturday's edition of Cracking the Cryptic, where today we're going to be looking at a puzzle by Mr. Menace. Mr. Menace is a fantastic constructor, and the puzzle is called Sum 41. And looking at it, I guess this is something to do with these diagonals that are labelled with the number 41. So today's secret is obviously not going to be 45. Hopefully it'll be something to do with 41, although I'm not exactly seeing what. We shall see. Anyway, I'll read the rules in just a moment. The testers, by the way, say that this is a work of absolute genius, so we should be in for a treat. Now, my only news today is I want to say congratulations to more of you who've managed to solve the Star Wars Sudoku hunt, which is available right now over on Patreon. So if you're a patron of the channel, please go over there and check it out. It is Peter C Hayward's masterpiece. And the successful solvers are Steve Meadows, Finola and Mateus, Andrea Pechera, Harrison Bear, and Yolanda Booking. I'm not sure how quite to pronounce your surname, Yolanda, but I hope you'll forgive me if I've got it wrong. But all of you correctly submitted the name of the next trilogy, so well done on that. Yeah, and that's all I've got to say. So we should get on with this, shouldn't we? So what are the rules? Let me read them to you. Normal Sudoku rules apply. Digits along an arrow in the grid sum to the digit in that arrow's circle. So that means, for example, those two cells, let's say that this was a 4 and that was a 5, then 4 plus 5 equals not 0 but 9, so that would be a correct formulation of this arrow clue. Clues outside the grid give the sum of the digits along the indicated diagonal, so we sort of already suspected that from the 41s, and digits can repeat along diagonals if allowed by the other rules. So in making this total of 41, what we could do, in fact you can see what we're going to have to do, because we've got a short stubby arrow here which is telling us those two digits are actually the same. So obviously there must be a repeated digit along this 41 diagonal. What you can't do though is, for example, that won't work because of the rules of Sudoku. Can't repeat a digit in box 2. Do have a go at the puzzle. The way to play, as always on Cracking the Cryptic, is to click on the link under the video, and that will take you to a page that looks identical to this one, where you can play the puzzle on whichever device takes your fancy. And now I get to play. Let's get cracking. Now these arrows are actually not particularly interesting. Normally a 3-cell arrow is quite potent, because if these digits were all in the same row or column, we could say they all must be different digits and therefore would add up to at least 6. So we could put a 6 into the circle, but here, look, you could put a 1 here and a 1 and a 2 here, and that arrow would only add up to 4. So I'm not prepared, I'm afraid, to pencil mark this cell as being 4, 5, 6, 7, 8 or 9. There are some people who might pencil mark that extensively, but not this person here. So is it the 41s or is it this 57? 13 in 4. 13 in 4 cells is slightly lower than the average digit. The average digit in a Sudoku, of course, is a 5. We're selecting from the digits 1 to 9, so there are exactly 4 digits lower than 5 and exactly 4 digits higher. So on average, if each of these was capable of being an average digit, you'd expect something around 20 for a 4-cell diagonal. So 41s. Let me just highlight the 41s again and stare at them for a moment or two. They do form quite a pretty pattern. And there's definitely something geometric going on there. I don't understand what it is, but if I just highlight these cells for a moment, yeah, that's weird. None of these purple cells overlapped. So when I highlighted them, look, they all just miss each other. This diagonal doesn't overlap at all with that one or with this one. And what we're left with is cells that are on the circled cells of arrows. And I can see, obviously, those two squares, by the rule of the arrow Sudoku, add up to the same as that one. So I'm just wondering whether or not, yeah, it's the same here. That's weird. That's weird. Oh no, I see. Look, if I add the 57, I was going to look at the 57 separately. In fact, I'm going to just check the 57 first anyway, because that looks like it must have a whopping great average. There are 7 cells on that diagonal, and 7 eighths are 56, which this diagonal averages over 8. Good grief. But what I'm actually looking at here, which I think might be more, or at least interesting, is if I highlight this diagonal as well. Now I have a very peculiar pattern in the grid, because none of these purple cells hit another purple cell. You can see the 41 diagonals don't overlap. With the digits on this 41 diagonal are all different. The digits on the 57 diagonal are all different. So each purple cell has just been flagged once when we highlighted them. But I can move all of these circle digits into the boxes, and that looks interesting. I'm not exactly sure what that's doing, but it's just leaving these cells, which are all arrow cells. Yeah, so I mean, what I'm expressing and articulating particularly poorly, but I'm sort of getting my head around it, I think, is that the sum of these diagonals, so the sum of, what's it going to be? It's going to be 3 lots of 41 and 57 could, rather than being the cells, the purple cells, which are their sort of the natural totals from highlighting the diagonal, if I was to remove the circles and replace them with the yellow digits, that is also the sum of 3 lots of 41 plus 57, because this cell and this cell, which are on the 57 diagonal, obviously add up to the same number as the 2 digits on their arrows. So by deleting these from the diagonal and replacing them with the yellow cells, it's still true to say that these cells, oh hang on, it's all getting confusing now because it's overlapping with the 41, but it's still true to say that those cells there that I've just highlighted, those cells sum to 57. And over here, on this 41 diagonal, it is true to say that, hang on a minute, that one, 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 and that one sum to 41. Because all I've done is replace the circles with the yellow dominoes. So, what is the sum of 3 lots of 41, 123, and 57? 180. I was not expecting to get. Hang on a minute. No, okay, no, that's all right. That's all right. I wasn't expecting to get 180 because 180 was what I thought we were going to be working up towards because, of course, box 2, if we add, yeah, this is where the secret today may not be 41 but 45. What is the sum of any complete box of a Sudoku? Well, any complete box will contain the digits 1 to 9 once each. So, if you add up the digits 1 to 9, you will get the number 45. So, that box, plus that box, plus that box, plus that box will equal 4 lots of 45, which is 180. And this is why I was confused, because we've just worked out that the sum of the purple plus the yellow cells is also 180. So that means that if I deduct those 2 purple cells and replace them with these arrow cells, so I want to take these out and replace them with the green cells, I should get back to 180. In other words, those 2 cells, whatever these 2 cells add up to, is exactly the same as whatever the green arrow cells add up to. That's amazing, actually. That's so cool. I'm just going to go through that once more, just in case anybody's confused about what I'm saying here. What I'm saying is that the purple and the yellow cells sum to 180 because that's the total of these diagonals, having shifted them about a bit using the arrows. But it's also true to say that these complete boxes also add to 180. All of those cells plus all of those cells plus all of those cells. And the only way that those things are reconcilable is if these cells, which are on the diagonals and form part of the 180 that when we were adding the diagonals up, if we subtract those two, so we're going to try and convert the diagonals sum into the boxes sum, we're going to have to take these out because these are in the diagonals and replace them with green, which were not in the diagonals, and we should get back to 180 in doing that. So those two must, so if they were an 8-9 pair, they must have the same sum as the green. Sorry, let me finish my sentences. So that's 17, which is impossible because actually, now thinking about it, there is one property I know about an arrow, and that is that if you think about the sum of any individual arrow and you include its circle in the sum, it must algebraically sum to 2x. Because let's say that this is an x, whatever's in the circle is an x, you then know that the arrow cells themselves sum to x, so the sum of the whole thing is 2x, and 2x is an even number. Now 17 is not even, so the most you could put into there would be 9 and 7, which is 16. Ah, that's so beautiful. Oh, that's it. That's it. That's it, because that's the most I can put into these two squares. I can make them add up to 16. What's the minimum I can make the green cells add up to? Well, the minimum would be if I put 1 here and 1, 2 in here, and 1 here and 1, 2 in here, which means that the circles are adding up to 4 in both cases. So this is summing up to 2 times 4, which is 8. This is summing up to 2 times 4, which is 8. So that together they add up to 16, and that's the most I can make these purples add up to in the middle box. So we have a break in, and we have the central digit, which is a 1. In fact, that was my central digit yesterday, wasn't it? Which I got via a jellyfish. So yesterday and today we have managed to get the central digit of the puzzle using the medium of madness, frankly. This is completely crazy. Now, what does that mean? So that means 4 has to be in one of those 3 cells, and 2 has to be in one of these 3 cells. No, okay, I was wondering about this diagonal, because remember this diagonal still has to average very close to 8. But actually what we've done there is not really put any pressure on that at all. If this had been a low digit, that would have put pressure on it. So where is the pressure coming from? We've got the 13 diagonal here. That square now can't be a 1 or a 2. 3 plus 2 minimum, that's 5. So those squares have to add up to 8 or less, which is not actually restricted, is it? Well, not in a way that looks meaningful. What about this quadruple adding to 28? No. I mean, it's a slightly high average. I feel it must be this 57. The 57 is by far the most constrained. Oh yeah, okay. Okay, maybe that's how we think about this. So, yeah, I'm not sure about the maths on this, but what I would observe in general is that 57 diagonal is a very high selection of digits. Now, there's a 41 diagonal that doesn't overlap with the 57 diagonal, that is also relatively high, because those squares have an average of very close to 7, because 41 divided by 6 is very close to 42 divided by 6, which is very, well, in that case it's 7. So these have to average 7, but these have to average 8. So these squares ought to be under pressure. 24, 17. 17 would be the absolute minimum I can put into those 3 squares. So 22, so 25, sorry, not 22, 23, 20, I'm going mad. 20, not 25, 45, 20, right, we've got 24 would be the maximum I could put there with 7, 8, 9. So these would add up to 17. 17 plus 5 is 22. 45 minus 22 is 23, and that is the minimum. Or is that, sorry, is that the minimum or the maximum? That is the maximum I can put into those, 23. Which means that that then gets folded out here. So the maximum size of those 3 digits is 23. I see. And then we can do the same thing here, perhaps. So we've got, if we put 7, 8, 9 there, these are 17 as well. Which means the maximum size of those squares is 17. Well, it's 45 minus 17 minus 1 plus 2, which is 25. So the maximum size of these 3 squares is 25. So 25 plus 23 is 48. Oh, that's beautiful. Good. This is so clever. Right. So these 3 squares had a maximum value of 23 by sort of unfolding the yellow. And unfolding this yellow in the bottom, by which, and sorry, I might not be being, I feel like I'm being completely inarticulate today. Let me do this longhand, because actually I can now write this in as a 7, 8, 9 triple. I can do the same here. So these 3 squares have a maximum value of 24. So these 3 squares have a maximum value of 17. 17 plus 4 plus 1 is 22. So these would be 23 in that instance, and they cannot be any more than that, because as I lower these down, these will get bigger, and that will reduce the value of these cells. But of course, these cells adding up to a maximum of 23, these 2 are just the same as this one. So those 3 squares there, let's use blue for that, these blue squares have a maximum value of 23. We do exactly the same down here, so we can maximize these as 17, plus 1 and 2 is 20, so these have a maximum value of 25, which means those have a maximum value of 25. 23 plus 25 at a maximum is 48, and therefore this square must be at least 9, and it can't be more than 9, so it is 9, and that's a 9, and that's a 7, and that's not a 9, and that's not a 9. And that's a 7 or an 8 by short stubby arrowness, and that's not 7. So that's 8, that's 8, that's 9, it sees 7 and 8, that's 7, that's 9, because it sees 7 and 8 in its row. So all of a sudden, the digits are flowing here. Come on, digits, flow some more. Let's... where do we look now? It was going so well. Oh no, I was going to say 9 in box 8, which can't go on the arrow, but it's got to go in one of those 2 cells. What we need, these 3 cells definitely do add up to 25. So those, yes, okay. So these 3 squares and these 3 squares add up to 17. So if that's a 9, these 2 squares have to add up to, sorry, if that's an 8, these 2 squares have to add up to 9. They're not 1, 8, they're not 4, 5. So this is either 2, 7 or it's 3, 6. And that's almost worthy of a bobbins, isn't it? Because that's not actually restricted at all. 7 in box 8 goes here by Sudoku. That's on the 13 diagonal. Okay, here we go. So that can't be a 7 or a 6 now, because if it was, you'd have to reduce these either to 0 or negative numbers. So if that's a 3, this would be a 1-2 pair. That would be a 1, and that would be a 2. 7, 9 means these have to add up to 4. So there's always a 1 in this not domino, but these two diagonal cells always have to have a 1 in, and because of this one, it has to go here. That square is a 2 or a 3. That square is a 1. That square is a 2. These two squares have a minimum value of 7, 3 plus 4. But they can't be 7 because that 7 would rule that out. So this square must be 8 or 9. Don't know if we can do anything with that. I'm not sure. 8 in box 5 has to be in the same positions as 2's, look. Oh, that being a 2 or a 3 means that these cells had to add up to 9, so that's got to be a high digit. That's got to be a 6 or a 7. These two squares as well are interesting. They have a 1-2 pair in the box, so they're at least a 3-4 pair. This is at least a 7. But it can't be a 9, so that's a 7 or an 8, which might be interesting. 7 or an 8. So, yeah, okay, so there must be a 3 on this arrow, because if there wasn't, it would be a 4-5 pair minimum, and that would take it up to a total of 9. So this is either 3-4 or it's 3-5, but there's definitely a 3 on it, and that's not a 4, look. So this square is a 3 or a 5. How do we do this? I feel like we're right. Oh, maybe we have to colour the 2's and the 3's, look, because these must be different. Because we've got 8 on the diagonal, so these are adding up to an odd number. So one of these is a 2, one of these is a 3. Although I haven't got any other instances of 2's and 3's yet. So let's just see if we can do better. Can we... I'm not even sure where to look, to be honest. What is the natural next step in this puzzle? Is it, oh, the 28 diagonal? I've now got 2 9s on that. So those two squares have to add up to 10, and they can't be... They could be anything. They could be 1 9, I think, 1 here, 9 here, 2 8 in that 8 here, 2 here, 3 7 with a 3 here and a 7 here, and 4. Yeah, so every single option for making 10 in 2 digits is available. But each one of those options is only available in one direction. Okay, right, I'm totally nonplussed now. I thought it was going too well to be true, so we're going to have to think harder, I think. Come on, brain, think harder. 2, look, must be in one of those 2 cells. So 2 is not in that one after all. So 2 is in this domino. If 2 wasn't on this arrow, this would be at least a 3-4 pair. So this would be that would be a 7 or a 9. Again, sort of feels possible though, doesn't it? So is there something else we've got to do? What about this diagonal? Because those 3 had to add up to 17. Though we know those had to, but so did those. So these 2 have to add up to 10. Oh, that's better. Yeah, here we go. These two have to add up to 10. They can't be 1, 9, 2, 8 or 3, 7. So that's got to be 4, 6. And that's useful. So that's 4. That's 6. Which means that's 9. Just unwinding our pencil marks. And that's not 4 now. The remaining cells we've got to place in box 8 are 3, 5 and 8. Aha! Right, you can't put 8 down here because 8 plus 3 is at least 11. So the only place 8 can go in the box is there, which places 8 in the middle box. Oh, lovely. And now I've got 8 and 7 placed in box 6. Come on. Now those two squares are 3 and 5. They therefore do add up to 8. 8's locked up into the corner of box 3. This square's now a 7. So that domino is a 3-4 pair, and that seems to only be available in one option, in one order. This 3 has given me a 2 here. These had to add up to 9, so that's a 7. 1, 2. This domino now has to have a 3 on it, because otherwise it's at least a 5 and a 6. So it's either 3, 5 or 3, 6. So this, oh, right, okay, look, this square is either 8 or 9, therefore, and it's not 8 by Sudoku. So that's 9. This is a 3, 6 pair. Therefore, those two squares are a 5, 9 pair, and we can see the order. We can place the 9 here, we can place the 5 here. I'm going to check this diagonal now works, actually, because we've just finished it. We've got, what have we got? We've got 2 8s, that's 16, plus 4 9s is 36, 52, 57. Perfect, it does work. That is a relief. So the world does seem to be in order at the moment. That's got to be a 9 in one of those squares. Now I can do my 13 diagonal. We know those two digits have to be different, so that's got to be a 3. 3 is in one of these two cells by Sudoku. And I must have now nearly done. We now know what these two squares add up to, don't we? Because we've just got to complete box 6 with 5 and 6. 2 in box 5 by Sudoku is there. This, yeah, okay. Now look at this column. This square needs to be a 3 or a 5. Well, it's got to therefore be a 5. It sees 3, so that's a 3, that's a 5, that's a 6, that's a 5. These squares here are 3, 4 and 6, which somehow is not resolved, which is a bit strange actually. There's a 4 here though. Okay, so we get a 3, 6 pair there, a 3, 6 pair here. I'm not sure whether it's this arrow or this diagonal. I'm going to check this diagonal now. Those two had to add up to 10, didn't they? So, have we ruled out anything more? We cannot. We can't put 8 in either of those two squares, so it's not 2, 8. And it's not 1, 9, because we've got a 1, 9 there looking at that square. So it's either 3, 7 or 4, 6. I'm not sure. I know that's not 9, so that must be 9. That would be 7, that would be 3. That would be 4, that would be 6. Now, is there anything Sudoku-wise wrong with those options? There probably is. I'm not seeing it. It feels like this must get resolved. No, I'm sorry. I can't quite see whether that's done. Right, so let us assume that I'm not missing the plain obvious in sight, and let's try and look at these squares, which have got to be 3, 5 or 6. And therefore these squares, which are 2, 3, 5 or 6, and they are not 5. Okay, so yeah, this square must be under pressure. Look, the minimum that domino can add up to is 5, but this square itself can't be 8 or 9, so this is 5, 6 or 7. So that can't be 6, because then it would have to tie up with a 3 to make 9 at least, and that's not capable of being 9. So this is a low number. Yeah, okay, and that number is not a 3. Because if you put 3 here, you can't combine it with anything there. If this is 3, this can't be also 3, so this has to be 5 or 6, and that blows the total. So that's a 2. This square here is still not 6, it's not 6, it's 3 or 5. So this square here is 5 or 7. Still possible. That's really weird. Let us... What does that mean then? So which diagonals have I not done? I've looked at the 28. I've looked at this arrow. I've done that one. I've done that one. I've done that one. Aha. What I've not done is completed this one, look. So at the moment we've got 25. So these squares add up to 16. So if that's a 7, they have to be a 3-6 pair. That would work. And if that's a 5, oh, that's a 6-5 pair. That works. What? What? 7, 5. There, it does work. It works both ways. I don't think this 41 is useful. This is not the new secret. It's just not. Okay, let's go back to doing Sudoku. Let's see if Sudoku can save our bacon here. 9s have to be down there. Oh, 8. Look, I can put 8 into box 7. It's got to go here. So I can nearly put 8 in box 1. Now this row looks interesting all of a sudden. I've got to put 3s, 4s and 5s into it. So this square's a 4 or a 5. 3, 4, 5, that's not 5. Oh no. 7. Where does 7 go in this box? Answer, only one place. That's a 7. So 7 in box 1 is in one of 2 places now. And this column looks interesting, doesn't it? We've got to put 1, 4 and 5 into it. So that's almost very nice. 1, 4, 5, 1, 5, 1, 4. Yeah, there we go. So if we look at... Yes, where does 5 go in column 1? It can't go here, so it must go up here. So this can't be a 5. That's got to be 7. And therefore this is 5. Therefore... that's not 5 anymore. So the 5 in column 1 goes exactly there. Which means this square must be a 1. I suppose this 4 was also, if I just used my brain, I could have seen that this was a 4 immediately. That's a 5 now. So we've got a 3, 4 pair over on the right hand side. And the remaining digits we need to put in there are 2, 6 and 8. No, 2, 6 and 9, forgive me. 2, 6 and 9. 2s, 4s and... so where does 4 go in column 3? It can only go here. So this square becomes a 2 or a 6. That's a 3 or a 6. 4 is still not quite dealt with. So the only thing we've not yet dealt with then... Oh, I know how to do this now. Look, 7s. There are 4 7s looking at box 3. Whenever you get 4 of a digit looking at a particular box of a Sudoku, you can always place that digit. The only place for 7 is here, which means that square must be a 3. That's gorgeous. So 3, 4 and 4 go in straight off the bat. Now, can we keep that going, or is that just going to peter out? No, the 3 is nice. That gets us the 3 and the 6 in that box, the 6 and the 3 in that box, the 3 and the 6 in that box. This 6 is giving us a 2 here, so that gives us a 6 down there. 2 and 9 might not be resolved, but what about these cells at the top of column 2? We need 3s, 6s and 8s, so that's an 8 by Sudoku. And the 3 is now useful, so we get a 3 here and a 6 here. 6 in one of those, along with, that's definitely not an 8, that must be a 1, which means that's an 8 and that's a 6, and I think we're tidying up now, aren't we? We need 2s and 5s into those squares. So that's a 5, that's a 2, that's a 2, that's a 1, that's a 1. This column needs a something. I have no idea what. I think it's a 5. And this column needs a 9, and that's good because that's going to get me the 9 and the 2 and the 2 and a 6 perhaps. We might have just finished the puzzle. I think it looks good. Let's click tick. Yay! Yes, that's really beautiful. Just a gorgeous idea executed with just panache from Mr. Menace. I loved the break into this. The fact that you can sort of fold the arrows up into the boxes and work out this trick with the 180s, and then almost unfold them again in order to work out how this diagonal worked. I thought that was gorgeous. It was just gorgeous. That got us the 9 here, didn't it? Can't quite remember how we took things forward after that. I think I messed about for a while, whereas I could have realised that those 3 squares added up to 17 and therefore were really restricted, especially once you got the 7 here. So there's definitely ways you could have done this faster. But yeah, never mind. I don't think 36 minutes is a disgrace on this one. It felt like the whole idea around the geometry at the start was, well, it was worth bathing in. It was worth luxuriating in. Let's put it like that. Hope you enjoyed it. Let me know in the comments. I do enjoy them, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.